Hey, hi everyone, welcome. So myself, Shubhrat Bonik, and I have three of my colleagues along with me, as it appears in the order, Sheng, Maulik, and Tung Lun. We were here to give a session on MicroPython-based interactive platform configuration for Coreboot. Unfortunately, we could not able to accommodate one of our colleagues today with us due to time constraint. So we'd like to acknowledge Maurice Ma for his contribution as well. So having said that, let us enter into our first slide that talks about maybe the session flow for the day, right? So I hope you can see my next slide. I just move to the next one. So how we kind of define the session for the day is maybe we will drive you to the problem statement. So first three bullets, we'll try to highlight the problem statement. We'll try to work our audience along with us to understand what is the problem, what is the gap that we discover, and as a team, we try to solve that. So in that process, the next bullet will talk about the solution part, and my colleagues will help you to drive into the more detailed solution. So we figure out the three best possible solutions, and then further we'll look into some future scope, how to translate this idea to reality, and then followed by some reference material that covers the source code, design document, etc., etc. And finally, we have a small announcement to make. So hope you will have a happy listening next 30 odd minutes, and this will be a good journey for you. So let's move to our first deck. Okay, so let me adjust this one a little bit. Okay. So this slide will talk about a boot firmware, as we are all here familiar with the firmware and all. So boot firmware is nothing new to us, right? So we know the boot firmware is maybe a piece of code that responsible to perform a very essential minimal hardware initialization, and only job it is up for here to transfer the control to the payload to boot further to the OS, right? So we'd like to take here example of Coreboot being one of the popular open source firmware. So Coreboot, as name suggests, essential stripped down firmware to perform the platform booting thing, right? And it is very committed to hardware, underlying hardware. It just focus on a fixed hardware configuration, try boot as soon as possible, right? So this is a picture that mostly you are all aligned with, right? But let me try to bring a different idea into it based on our past experience and present experience, right? So over the decade, platform enabling model has changed, right? So what I mean by change is that maybe a decade back, the typical platform turnaround time was 2+ years, but currently it kind of shrink to maybe 3 to 4 quarters at max. That means people are looking forward to more faster enabling the and then engaging to the scaling team, maybe ODM, OEM as soon as possible. And in order to do that, they want to have complete validated, tested solution that they can share with their partners, ODM, OEM, for the further scaling. So this layer that we highlighted here is try to talk about that verified tested layer, right? So the verified tested stack that every product team want to develop is combinations of three things: hardware, then boot firmware, and then kernel, right? Hardware is essential piece, and hardware may be combinations of the different hardware component. And as you all agree that a single hardware component maybe have its own maybe possible different interfaces that a firmware or the bootloader supposed to configure to find out the exact hardware interface that satisfy a different ODM and OEM need. So if we just take an example of the audio IP, for example, here, audio can be possibly configured in any of these three interfaces: HDA, Soundware, or the I2S, right? So based on your final design, so you like any ODM or OEM should be speaking maybe I2S, or somebody may be speaking HDA or Soundware, right? So what essentially that means is that when we are kind of sharing this stable stack with our partners, different OEMs, we should be ensuring that the validation is thoroughly going through all the different possible hardware interfaces, right? And like firmware or the boot firmware is the essential piece that brings this hardware into life, right? So this all boils down to being boot firmware intelligent enough. Do this guy empower enough to configure those hardware interfaces? Do this guy is able to communicate with the kernel layer? Just give one more example, right? So today, I think many of we all using the your hypervisor and then virtual machine, right? So virtual machines typically has a different mode of configuration. maybe emulation mode, maybe the pass-through mode. So these are the configuration that your underlying hardware, to access the underlying hardware, and your bootloader need to understand that. So like we are just kind of preparing here to maybe summarize here is that between kernel to bootloader and further bootloader to the hardware, we may need this two key layer that we call as a configuration layer. That configuration layer helps you to scale your design, right? So maybe having a fixed configuration is not what industry is needing nowadays. They may need a stable configuration that is well tested with all possible hardware combinations and configuration that we can provide to our partners, and they can immediately start enabling that without much changing the source code aspect. They need to deal with how do I change my hardware configuration from A to B, right? And again, coming to this real world example, we try to capture a Chrome design, reference design. There is Voltaire, this is Tiger Lake based, and these are the below are the your scale design. So first, you need to have a validated maybe package given to our partners, and then they start enabling on that. And for this purpose, I think we kind of provide the ample background why we need this configuration space between these two layers, right? So all over this talk going to be on this requirement of the configuration and how configuration is chronicle in modern days enabling model, and how it became more chronicle when we work in the open source firmware development aspect, right? I hope we like most of you are agreeing with me that configuration is a key when you want to scale more design. And in next slide, we'll see how it is more evitable when we are working in the open source firmware development model. Okay, so moving to the next slide. So this is a firmware development model that typically we kind of portray here, open source Coreboot development model, right? So this model is little different than what industry was evidencing last several decades, right? So typically journey from the closed source to open source is now maybe very evitable, right? So in the closed source model, you don't really bother about engaging multiple partners. Maybe a single company owns the entire firmware development. But goodness of open source, we have a kind of a modular development where the like several different folks coming from the silicon team, coming from the SoC team, Coreboot team, and maybe the partner team, right? What we shown in the earlier slide, that your voxel, your to-do, dev-lane. So those are your ODM and OEM design. So they are coming, and we are all together try to create a single package, right? So for that, these are kind of, you see in this picture, so these are the modular approach, the FSP, SoC, and mainboard, and those are maybe developed at their different time space, right? So what this all about? So all this all about means a modularity, and for the modularity, we need to have a API-based communication between this, right? And for the API-based communication, the key is your input parameter, right? So that tells you how to configure hardware interface, right? Until and unless this firmware or this individual component are modular enough to accommodate those APIs function call, right, with a given input. So what might happen is that your mainboards team might be started looking into your SoC code to understand, hey, if I want to change maybe my mainboard configuration versus X to Y, do I have a proper hooks implemented in SoC, or I need to implement that, right? And then what happened, your silicon team or SoC from team started looking into your FSP as a sample code, right? So this is all good. People got opportunity to learn, right? But what we are maybe missing here is the enabling time, right? And the time is money. So in this faster enabling world, we really do not have a luxury to spend more times on looking each other's code and try to figure out mistake or try to fix those, right, in the time when you have to ship the product. So for all these things, I think this is a very key reason why we need to understand that modularity is key, and each modular aspect is providing with a thin layer of configuration, and that is what maybe we pass the information from one layer to other layer and vice versa, right? So this is the like whole essence of this. We hope we could able to provide a good high level picture, understanding how the platform enabling model change, and for the platform enabling model, how the open source development model plays an important role, and where is the gap, and why we need the configuration, right? So with that, I think we kind of heading towards the configuration requirement. So as this term configuration suggests, that it is basically meant to create something shape, right? So and the shape is means we kind of try to explain in the embedded world is that shaping our schematics to the multiple schematics, right? So how you use this configuration to make sure that you have make your embedded system configured enough that from your firmware layer you can enable, disable certain hardware interface or certain other features, right? Without really going into the source code level, knowing how actually you should be doing all these things, right? So we would kind of try to eliminate the dependency of being a firmware engineer at the place always, right? And we try to empower more our partner team, maybe a validation engineers, silicon engineer, silicon validation. So all sorts of our ingredient team, right? So if you pay attention to this right-hand side picture, so this is typical sample configuration taken from a IA code group. So at high level, we have different verticals of configurations, right? So FSP configuration, it talks about the underlying SoC layer that provides you various enable, disable options of the hardware interface. Followed by, we have the firmware configuration layer. This is predominantly your main board layer configuration, where you say, I have a X vendor codec versus the Y vendor codec, which one I should choose between the two different schematics. Third is your strap configuration, which is pretty much in a control of the silicon vendor that they want to fuse or unfuse certain features, right? And then finally is the kernel configuration that we give an example of your virtual machines and whatnot, right? So we have these four verticals on this one. And for the interest of the time and this content, we'll try to mostly focus on the anything that touches the silicon, right? So FSP configurations or firmware configuration is something that we'll touch as part of this session, right? So now, if we just connect back to our very first slide, when we talk about the working principle of Coreboot, what we talked there, we talked about the Coreboot is committing to perform a minimum hardware initialization and ensure the platform booted to OS as soon as possible. But now, if you think that isn't this kind of limiting us to scale beyond a fixed configuration, right? So we are like, maybe this working principle is perfectly fine when you're talking about a fixed hardware configuration and all, but now when we have a goal in our hand to scale maybe 1,000 odd devices or the different combinations in our hand, right? So then we need somewhere this configurability, right? So this session is all about that, right? So today what we are lacking is that the configurability that Coreboot provides, it is pretty much limited to your source code level changes. That means we are kind of disengaging our the other partner team, validation team, or the integrations and other engineering team. Those mainly not having a firmware background, they may not feel very inclusive in this case, right? And when we are discarding them, we basically limit the innovations and maybe do something things very nicely, right? So we like to for the purpose of this session, to make everybody in a close proximity and empower everybody, where without knowing n-level details about a firmware, how the source code getting compiled and whatnot, right? They should be able to play with the hardware, underlying hardware. They should be empowered enough to enable, disable certain hardware interface and deliver a solid tested hardware to the partners. So having said that, I like to pass control to my colleague, Tung Lun.
All right. Okay. So yeah, thanks Subrata for giving a very solid background on what we're going to cover for this presentation. So this slide, we're gonna go into a detailed scoping of configuration specifically in Coreboot, in a context that all of us are very familiar with, right? And of course, this also is applicable to Slim bootloaders and other open source bootloaders. And the proposal here that we want to show is we want to provide and lay out all the possible ways to potentially configure the hardware interface, right? So this can benefit a lot of different functional engineers, as what Subrata mentioned, whether you're working on silicons, platform enabling, validation, or integration, right? So we want to be able to provide such interface that is so easy to debug and enable new platforms so that it can scale across any new solutions and we can achieve a better time to market, right? So here you look into these slides, there are like 3 different configurations, parameters that we kind of lay out as a high level overview. So first of all, we look into specifically on the bottom left, the FSP static configuration. So for this one, the the first 2 points, we kind of want to highlight that we actually have some open source friendly utility solution in the EDK2 repository. So this is actually called a config editor. So you can actually go check it out. We have the link at the reference session. So this utility actually allows you to configure all the inter-FSP that's already in the market today, and it's written in Python, right? So we open source all the source codes and the steps on executing them, and later we even have a very nice demo for you to see, right? So here with this utility, you can actually edit all the FSP configuration regions directly into the FSP binaries. So you can imagine, you have the FSP binaries, you've got the headers, right, and the PSF files or YAML files. You can actually use this utility to change any parameters. So of course, the advantage with this is that you can easily patch any FSP provider's silicon policies, right? So if let's say you have let's say you have a Tiger Lake with you, right? So you want to change some memory configuration or silicon configuration, you can easily do this, patch the binaries. But unfortunately, after that, what you need to do is you have to take that patch binary and recompile with your bootloaders, right? So for example, if let's say you are using Coreboot or Slimboot, right, you have to replace the binary that was patched. So this is the kind of the disadvantage. And another disadvantage is the bootloader could somehow accidentally override some of the defaults, right? So maybe some customers could run into some frustration that, hey, why am I changing a certain parameters, but I expect it to take effect, but it does not, right? So maybe some source code is overriding such configurations. Yep. So that concludes for the FSP static configuration, and in the subsequent slides we also have some more details. And moving on to the middle, which is the host-based configuration. So this is the configurations that actually allows the Coreboot binary level modification. That means we're essentially changing the content of Coreboot, but we kind of want to have that kind of hardware and software interface that being configured in this process to remain persistent across multiple reboot and sleep states. So many of you could already familiar with like kconfigs, right? You change some enable or disable flags, right? You can easily enable or disable some features. So this is what we are talking about here, right? So the advantage here is it's source code independence, right? You don't have to go and change any source code. You can easily toggle that switch, and it's kind of scalable, right? So you don't have to have that source code knowledge to make that modification for the feature itself. But the disadvantage is it has to take place at the host machine, right? So not everybody actually have a Dediproc handy, having to refresh the firmware to the board, right? So that's kind of the disadvantage here. So having this context, so we actually with this presentation, we want to introduce a DUT-based configuration, right? Sometimes something that is quite easy to actually be able to solve some of the problems with the host-based configurations that I was mentioning just now in the middle. So the right side, right? So we are talking about a MicroPython configuration editor, right? So this DUT-based configuration could actually run on the DUT itself. It's sort of like a BIOS setup menu, so it allows you to change your dynamic configurations. And we have the idea, right, to dispatch this configuration as a standalone payload. So you can choose, you don't want to load this payload, or is it something that you want to create like a value add service to your customers. So this is absolutely optional. And the advantage is this very lightweight and simple, right? So this editor can launch as a part of a payload to allow configuration. And in fact, later when we go into the details, you could see that there is some other use cases that you can also enable this, because this configuration mechanism is kind of like a Python based. So you can actually write any Python scripts that if you don't like a UI, right, you can actually do some other interesting use cases with any Python scripts, right? So the disadvantage here is, you're gonna need one additional reboot, after you update the configuration to get that configuration to take effect. Because if you think about it that way, right, if you change some settings, but the settings was already programmed before this, so probably gonna need a reboot to override that the things that you change. So it sort of functions like a BIOS setup menu that we are familiar with today, but it's kind of optional that you can easily enable or dispatch it. Okay, so this is the scope that we're going to cover, and I'm going to talk a little bit more into the FSP static configuration. And after this, I'm going to pass to our partner Maulik, to go into more other details. So looking at these slides, you're actually looking at the open source config editor that I was talking about just now, right? So at this UI, you can see that there is some parameters that you can configure. So these are actually the default FSP parameters that is already available in the open source. Right? So these tools is actually developed in Python. So if you're familiar with Python, so this is good news for you, right? You can actually go check it out. Play around with it. We have some extensive features that the previous closed source binary configuration tools. So this one is absolutely open source. So you are also welcome to contribute to this tool. We also have bug fix and additional features that we have in mind to implement it, get it better. With these tools, we can easily patch any FSP binaries. And also, with this patching, you can straight away modify the values. And there are a couple of good things about this tool. I'm not here to promote the tools, right? There's a lot of documentations that we have in the README if you check this out. But just to name a few, right? So you can actually save some deltas. So in case you want to keep track of what you change, there's a very handy delta files that you can use to see what you change there, right? So you can also directly patch the bootloaders. So for example, if let's say you already have your FSP inside your Coreboot or in your Slim bootloader, right? You can actually use this tool to directly load the binary and patch the parameters. But this is provided that if the parameter is uncompressed, right? So if let's say you already compress FSP binaries, then we might not be able to patch that particular region because the header could not be found anymore, right? So probably have to have the compress or decompress ways to do it. Yep. So that's all about the tools, and now I'm going to pass to Maulik to continue with the host-based configuration. So off to you, Maulik.
So as in the previous slide, my colleague Tung Lun has already talked about the static config editor tool. So in that approach, to summarize, we had the three disadvantages. One is that if you want to update the Coreboot binary directly into that one, you need all the FSP binaries decompressed. But as of current Coreboot implementation flow, we have the FSPS binary, which is currently compressed. So that is one drawback, that you cannot update or modify the FSPS related parameters. Second drawback was that if in the config editor tool, we need to have a separate config region. The reason being, currently we have the three copies of the FSP binary, RO, RW, and RWB. So either tool has to update all three copies, or we can have a single region where we can update everything. So to overcome all these disadvantages, we need to design a new flow in the Coreboot over the existing flow. And the third disadvantage is, as Tung Lun has mentioned, if Coreboot is overriding some parameters, then actually the user modification cannot take the effect. So to overcome all these three, we had the requirement to modify the current Coreboot flow. So if we focus on the picture on the right side, this is the current Coreboot flow. So this is just a flow of the FSP driver. So here is the example of FSPM driver. The same flow is also applicable for FSPS. So as you can see, once Coreboot is executing the FSPM driver code, what it does is it actually reads the default UPD values from the SPI. Once it has read it into the buffer, it passes that buffer to the SOC override code. So from SOC, it will override the UPD values based on the platform configuration. Then it will pass the same buffer to the mainboard code to override the UPD values as per the mainboard design. And once all this modification is done, then FSPM driver will actually call into the FSPM API with the updated buffer. So this is the current flow. So what will happen is, if user has modified the FSPM default values through the config editor tool, there are still chances that your SOC override or mainboard override code will override the value from the Coreboot code, and you might not see the impact. So for to mitigate all this, what we have done is we are proposing to create a new config region currently we will name it as a coreboot underscore config. And what will happen is our config editor tool will only parse this region. And the third one is we need to skip this override, and we need to take the values from the config region, so that it is always the value which user has modified and not from the code override. So this is what we are proposing, and we will also see the detailed flow in the next slide. Also with this flow, we are also planning to have fail-safe mechanism, which means if you have modified some values which is making our platform unbootable. So in that case, what will happen is Coreboot already has a mechanism of recovery. So when Coreboot is booting through recovery, it will clear this Coreboot config region so that you will boot with good bootable value which you have validated earlier. So that is our fail-safe mechanism. And one of the disadvantage, as we have previously covered, so every time you want to change the UPD value, you need to read the image from the host, modify it on your local machine, and refresh the image. So that is one disadvantage of this one. But otherwise, it avoids recompilation of the code. So to do some debug, it is much faster approach than what we currently have. So I will go through the next slide. This image illustrates the proposed design flow, and this is the first boot flow. So it means when initially we have a core boot image, so there will be an empty or placeholder configuration region. In this one, we will just put the FSPM and FSPS configuration region, not the entire binary. So what will happen is initially this region will be empty when you flash the image first. During the first boot, we will go through our original flow where Coreboot driver will read the UPD default values from the SPI. It will pass the control to the SOC and mainboard code to override the default values as per the platform requirement. So once we have a modified buffer, just before calling the FSPM API with that updated buffer, we will store all these good or bootable values to the SPI. So we will just call this update configuration and we'll write the entire buffer into the SPI. And then we'll call the FSPM API. The similar way we will follow for FSPS also. So at the end of the first boot, our SPI layout will look like this, where you have the FSPM config block and FSPS config block saved in the SPI with all the good values. So I will go to the next slide to see how the subsequent flow will look like once we have this layout. So in the subsequent boot flow, what will happen is now, let's say user has already modified the value. So now user should modify this config block FSPM and FSPS instead of modifying the original FSP UPD block. So once user has modified this and refreshed the image, once core boot control comes to the FSPM driver, instead of calling this SOC and mainboard override, it will first go and check whether there is a valid core boot config region existing. And that check we will do using the signature. So signature, let's say for core boot config, and another signature for FSPM. Let's say if it is a Tiger Lake, then it will be Tiger Lake UPD. So if that region signatures are valid, then what we'll do is we'll read back that config region from the SPI and just pass it to the FSPM driver. So there is no override. So that way we can avoid Coreboot code overriding the user modified value. And similar way we will follow it for FSPS also. So I hope the flow is clear till now. And we also have one demonstration in the next slide for this one. So for the purpose of demonstration, what we'll do is we are taking the example of CNVA device. So what we'll illustrate is we have already compiled a Coreboot binary with updated flow, which we had seen in the previous slides. So first we will flash the image and let it boot, and we will see in the PCI device list, we will see that CNVA device is available. Then we will read back that image to the host. We will modify it using the config editor tool to disable the CNVA for, let's say, any debugging purpose or anything. And we will refresh the image and show that it has actually taken the effect and CNVA is disabled. And here is the short summary of the steps which we are following. So you can quickly go through it. So we will first flash the image. Once platform is booted to us, then we need to read back the image. So we have the updated layout, and just open the image using the config editor tool. And one point here is we need to have one fsp.bsf file, which is of the same version of the FSP with which Coreboot has been compiled. So both should be in the sync. So once you have that, it is very easy to modify the any parameter or any value using the config editor tool. And we just need to save the image and refresh it and reboot the system. So now we will play the demonstration.
So thanks, Maulik, for the explanation on the host-based configuration. So basically, the DUT-based configuration, you can know it as a basic setup menu. So I'm pretty sure all of you firmware developers have used setup menu before. So it's very easy to use, and with the setup menu available, you can just change the parameter without need to refresh the whole image. So that's basically a very good tool for us. So over the years, Coreboot Coreboot community does come out with many setup menu. So what is the special thing about us? So from us, our implementation is pretty simple. So we are building on top of the FSP configuration block, which presented by Maulik just now. So you can see that since the configuration is block available, so you just need a way to able to fetch the data and change the data, and then make sure the system reboot and then reflect the change data with it. So how are we going to do that? So the way we do this is we have a setup menu script, which is based on Python. And with this Python script, you need to use the Coreboot to boot the file. That's why we are using the MicroPython payload with this. So this MicroPython is just a L file module, which is able to load any simple Python script. So with this loading up, with this script loading up, we are able to use this script to modify the FSP config blobs. And then once you change it, just like any setup menu, you just save and reboot and tada, and then that's it. So what we did is we are also utilizing the lib payload and also reboot libraries, quite similar to how depth charge works. So with this, then we are using the open source available libraries as much as possible without need to create more complications. So here, let me deep dive a bit into how we do it. So you can see the MicroPython, which is the deep blue color. It basically is a Python libraries translation layer to the C code. So that you can help it to map the low level functionalities. So what does that mean? Is basically provide a basic layer to interact with the payload C file when you use it. So go to the inside our MicroPython L file, we are utilizing the lib payload. So this lib payload, we will need to have the frame buffer, which is basic for display. And we also need to use the SPY read and write memory management and Coreboot table. So we can either create a whole SPY read and write and memory management stuff from the scratch as a driver in the MicroPython, but our implementation is we are using the Coreboot to pass the function pointers via the Coreboot table, and from that we are exposing to the MicroPython, and from that we are exposing to the config editor too. This is a setup menu Python script. So as long as all the drivers, including the input devices, support and stuff. So, and our Python script config editor, basically you just need to do what Python usually people do it, which is render the UI. And once you're able to interact with the function, so you need to able to read and write the config options. And also you need to make sure that you're able to detect keyboard, because sometimes you need to input the parameters as usual. So make sure the keyboard is detected. So basically that is the novelty that we presented using MicroPython with the lib payload and then the lib payload utilize those functions exposed via the coreboot table, and then from expose those functions to the config editor, and then config editor just use it as a background, and that's it. So it's quite simple as that. Okay, so we're going to show you a quick demo, and I think this is not complicated because like all the cell menu basically just set and then change the setting and boot up. But we'll show you the whole flow from basically the flow is starting from the after you fetch the coreboot image, and then after and you boot up and the cell menu will come up. So yeah, I'm going to share the video. Okay, so here we summarize all our current work out to date. And the future scope, which is what we're going to do after this, of course, is we're going to share our design document with the Coreboot mailing list. So the Coreboot community will feel free to come in and provide the feedback for our idea and probably improve it. And then, so in case that we can see how we can improve it, so we can also merge our changes into the Coreboot Garrett. So that's why we're going to upload our work in progress changes. So for your discussion and feedback at the same process. And we want to treat this proof of concept as a scope for designing the generic and unified payload, which deals with the hardware and platform configuration alone for all the popular bootloader. So this can be scalable because it's utilizing the Python script and also the config editor tool, and then with the FSP config data. So all kinds of vendors which utilizing the Intel platforms, they can just use it either the Coreboot or SimBootloader. So the novelty is the same. It's pretty straightforward. So that's why we want to propose not add extra layer or complication on top of it. So yeah, this is our reference. Feel free to go in and take a look. Yeah, now I'd like to pass the time to Subrata again.
Hey, hi. Thanks, Sheng, and thanks everybody for very nice presentation, and folks, welcome back. So this is, I like to share some good progress that we have done last 1 year. And as a result, we have 2 system firmware and open source firmware development books coming up from APRES, authoring myself and Vincent Zimmer. So we'd like to share this good news with you and hope you will like our effort. So I just like to summarize by saying that this book is basically written by engineers for the engineers. So once this is available, maybe by next month or very early next year, you can have a read and share your feedback. So yeah, till then, thanks.